Alright guys, so my first test I'm going to do is I'm going to test the rectifier regulator module, this module right here. And again, what this does is this takes the AC voltage generated by the alternator under the flywheel and converts it to DC voltage, and then also regulates it. In other words, it keeps that DC voltage at a steady amount so that as the engine RPMs are changing, the voltage isn't just constantly fluctuating. So there's a couple ways you could test this, but the most conclusive way to test it is to actually test it live, so to speak. In other words, the first test that I already did, which I did off camera, was I took my ohm meter, I set it to the diode or continuity check setting, and I put the leads here and here, and what I'm basically looking for is a dead short, and I didn't see one, or very low resistance reading. And then I went from here to the center, and then from here to the center. So I checked all three, and I didn't get any really low readings. That's a good thing, because a really low reading between any of these points to the other point, to any other point, tend to indicate that there was a component shorted internally in there. Now, this thing could be fried and it could be open. Then the only way we're going to really find that out is to actually do more of a dynamic test. And so what I've got here is I've got my Sencor PR57 power right, and what this is this is a it's a variac. It's basically it's a variac on steroids. It's got extra features in that, but the main function it is it's a variable transformer. It takes the 120 volts input coming in from the wall and allows me to vary the output on this outlet between 0 and as much as 160. This can actually go as far as step up the voltage. But what I'm going to do is I'm going to use it as a low voltage AC power supply. Now, if I didn't have the variac here, how could I do it? Well, I've got another variac that came with the Wells Index mill. That's the old-fashioned variac where it doesn't have any meter or anything on it. It's just a big auto transformer with a knob. Also doesn't have an isolation transformer, which this does, but I don't need an isolation transformer, and I'm not going to get into that. That's a topic unto itself. So if I didn't have this, I could use just a regular variac, and if you don't have a variac, you could probably find a low voltage AC power supply somewhere around your house, whether it's a junk AC adapter that you don't use anymore. I don't know whether or not the current that provides might be too low, but voltage wise you could probably find one. The other thing I've got is I've got some old train transformers from the old electric trains, and some of those are going to be able to put out the AC voltage and vary it right in the range where I want to be working, which, to be on the safe side, I probably want to be around 15 volts AC. Okay. And so what I've got is I've got the output of the variac set to 0, knobs all the way down. I've got the meter selected on current. This will show me the current draw of the load that it's hooked up to, which in this case is the module. So if I start to raise the voltage up and the current starts to go up really quickly, then I know I've got an internal short, and chances are if I raise the voltage up, this thing will just start getting really hot and maybe even smoking. But I would know right away that that thing is junk. So since I'm using this meter here to monitor my current, I've hooked up my Fluke DVM, set that to AC volts across the input so I can monitor what's coming out of the variac and going in. And then I've got my other Fluke DVM set up for DC voltage, but I don't have the alligator clip, so I'm just going to hold this on here. And the ground for the Fluke is the casing, because they're using the case here as the ground path. Let's fire it up. Okay, so now we're on, and with the variac turned all the way down even, it throws about 1 volt AC. So I'm going to now bring this up very slowly. That's 5, 6 volts AC. Still not drawing like enough current to even make the meter move, which is a good sign because there's no load on it right now, so I wouldn't expect it to actually be drawing current unless there was a short. Okay, so that's about 16.6 volts AC going in right now. I'm going to stop right there. And now I'm going to probe the output. I'm not getting a good connection here, probably with my ground. A little spot right here that I scraped it bare. I'm getting 16 volts DC out. So that's a little high. So this doesn't seem to be regulating. Just to show, if I put my meter across, or I put my DC meter across the AC input, you'll see it doesn't register anything. Just to show that I am in fact actually looking at DC voltage. So the rectifier is definitely working. I made an assumption that this is a regulator in addition to a rectifier. This may be strictly a rectifier. There may be DC regulation actually happening inside the Mercury switch box. So that's interesting. So I guess what I could do next is I could tie the DC coming out of here to here and then see whether or not it actually holds this down at around the 12 volt, which I would expect it to run at. Alright guys, same setup. I moved my meters up here because I needed a little bit more room to get to the screw terminals here. What I did was now I've got a jumper wire going from the 12 volt, the red connection on the switch box, to the red connection on the rectifier, because this is how it was wired in there. They had the 12 volts coming in from the boat, going here and then going there simultaneously. So essentially these are in parallel. So without a battery in this circuit, I'm not sure whether or not this is even going to work correctly. In other words, even if it still doesn't regulate, I wouldn't be convinced that there's necessarily a problem, because it might need a battery in the circuit. I know it sounds crazy, but I ran into this problem a while ago when I was diagnosing the one of the ATVs. I think it was the old Kawasaki Prairie, and it turned out the electrical system apparently didn't really have a problem with it, but I was trying to run it without a battery in it, and that was just making the whole electrical ignition system act screwy. So I'm not sure. Well, alright, so we'll proceed with caution. We're starting at 0 volts again. Matter of fact, see if I can't rig up a way to keep that DC voltage connection on there. Well, okay, this is a little better. I've got at least my positive meter lead mounted so that I only have to hold this on the ground connection, and that leaves this hand free. So again, we're starting at 0 volts, and you can see I'm up to 2.5 volts AC, and I'm getting 1.8 volts DC. No excessive current draw. 12 volts AC, 11.6 volts DC, 13. Okay, so this is still not, this is still not regulating. No, it doesn't matter what I put into this thing for, well, you know, I'm not going to push it obviously, but I mean, I ran this up to 18 volts AC in, and that's pushing 18 volts DC out, and nothing is pulling it down to regulate. Well, again, that could be a function of the lack of a battery in the circuit causing a problem, or the more frightening possibility would be that this is supposed to actually regulate the DC voltage and it's not doing it, which would mean that quite possibly it's been putting out an over voltage to this switch box, and the switch box may have fried. So the only thing I can think to do at this point is to continue with the testing of the switch box and just set my variac so that I get 12 volts. And actually, I might even just take this out of the circuit altogether, and I've got my 12 volt regulated DC supply, and I might just stick that on there. Oh, and actually that brings up a good point. What's coming out of here is AC at 60 cycles a second. So it's a pulsating, it's AC, okay? Alternating current. That's what comes out of the alternator. But on some of these systems like this, like on that ATV, it's relying on the DC, it's relying on that battery being in the circuit to help filter that DC. There's no capacitor to speak of. There's no filter capacitor here. So what's coming out of here is a pulsating DC. If we looked at this with a scope, what we would see is we'd see what would look like an AC waveform with the bottom half chopped off. So we'd be getting half wave or maybe full wave DC, and it would have basically a ripple to it. And then, if this was like in a circuit where we were using it to run electronics in a radio or, stereo or TV or something like that, it would be filtered. Well, this isn't being filtered. But what a battery being present in the circuit can do for you oftentimes is it can actually act to flatten out that waveform, to smooth it out, so to speak. All right, guys, I got my test set up now to do a live test of the actual switch box and ignition coil together. Okay, this is not going to definitively tell me if I have a problem with the coil or the switch box. In other words, if there's a problem with the coil or the switch box or both, this isn't going to tell me which one it is. But it will tell me, it can tell me whether or not they're both good. So if you follow my logic there. In other words, if this coil's bad, then this test isn't going to work, and I won't know whether or not it's the coil or the box. If the box is bad, the test is not going to work, and I won't know if it's the coil or the box. If both of these components are good, this test should produce a spark. So let me try and run you through the setup real quick. Okay, this side of the box right here is pretty much, might as well call it your input side. You can disregard this brown connection. I actually think there's something connected to this on my motor. I'll have to go back and check out what that is. I thought there was something on this terminal. But the red is 12 volts, and that's going to always have 12 volts on it if the battery in the boat is hooked up and all the wiring's hooked up and you don't have a battery shutoff switch. There'll be 12 volts present here. This white connection is only going to have 12 volts when the ignition key is in the on or run position. Okay? So what I've done is I've tied this red to white with this jumper so that I only have to feed the 12 volts coming from the rectifier to one of these terminals, and it's actually now going to both. So as soon as I energize my variac over here and start sending AC into here, I'm immediately going to be also sending DC into both of these connections. It will have the effect of that turning the thing on. Okay? On the this side over here, the distributor side, we have 3 connections. Brown, this, believe it or not, is white, and this is black. On the brown, this lead was connected to this little device here, which is called a tilt switch. And I think on these old ones, it's a Mercury tilt switch. And I don't mean Mercury as in because it's a Mercury outboard. I mean Mercury like it has the really deadly Mercury liquefied metal inside of it. The wiring on that is shot, so I've disconnected that. I believe the job of this switch is to ground this brown connection when the boat motor is tilted up out of the water to disable it from running. Or if for some reason something goes haywire and suddenly the motor, something happens that the motor flips up when it's not supposed to, it will kill the ignition. I believe that's the theory behind this. I've disconnected it because A, I don't know if it's good, and B, I know the wiring harness is shot on it. So for testing purposes, we're going to jumper brown to white. Okay, so these normally there's 3 wires coming from the distributor to go to here from the trigger inside the distributor. So for testing, we're gonna jump a brown to white. I've already done that. I've also taken a black wire, and connected it to the black terminal, and I've left that bare. This, when touched momentarily to the ground, which in this case is going to be the casing here, is what's supposed to actually act as the trigger and cause this to send the pulse to the ignition coil through this green wire that I've left hooked up this entire time, and the other ignition coil wire is the black one, which is grounded. The rectifier block is grounded to this. I've also run a wire, clamped the wire to the frame of the ignition coil that runs over and clamped it to the frame that everything else is mounted on, so that the frame on the ignition coil is grounded to the rest of the circuit. I'm not sure if that needs to be that way, but since I didn't know, I figured better safe than sorry. I grounded it. All right. The last thing I did was I took the high voltage wire, the high voltage lead that I had originally disconnected from the ignition coil and left on the distributor. I removed that from the distributor. That screws into the distributor, by the way, so you got to be wary of that. You have to unscrew it. Don't try and pull it out like a car, like an old car one. You'll rip it right out if you force it, and then you'll wish you hadn't. So anyways, you unscrew that. Once you've got it unscrewed, then you can reinsert it back into the ignition coil, which I already did. And you position this approximately 1/4 to 3/8 of an inch away from a ground, in this case, the case. That's where I'm going to be looking for spark jumping if this thing operates correctly. Okay, I've already preset my variac so that when I flip this on, I'll be putting 12 volts into the circuit. So the first thing I'm going to do is I'm going to flip the variac on, and I'm going to take a look and see whether or not I see any ugly current draw or smoke or bad noises or any of that. Okay, 0 current draw, no noises, no nothing, no smoke, no sign of anything getting ready to burn up. I've still got my lead attached, so I'm going to just double check and make sure I still have, and I do. I have 13.2 volts AC going in, and I've got 12.57 volts DC coming out. So we're live right now. So technically, if I come over here and I tap this black wire against ground, I should be able to generate a spark. Nothing. That is a doornail. Alright, one more check before I throw in the towel on this ignition system being junk. And that's going to be, I have now eliminated this from the circuit, but basically I just unplugged this, and I've now wired my 12 volt regulated power supply. I've wired that directly into, well, I've got it hooked up directly into the box here. So what that's going to do for me is that's going to give me a non-pulsating steady filtered DC source, which is going to be more of a better simulation of a battery. This has very low current capability, this power supply, so it might go into overload if it actually tries to make a spark. It's got an automatic overload limit, but at least then I know something's happening, as opposed to right now it's not doing anything. So I've got it set for about 13.8 or 14 volts DC, and I've got my meter selector switch on that power supply set to amps so I can monitor the current, and everything else is still hooked up the same way. I'll fire it up. Alright, no current draw, nothing unusual going on here. Still acting just like it was before. Pretty dead. Oh! Well, there you go, ladies and gentlemen. this circuit does not like not having a battery in there. Nice hot spark too. Okay. All right. So my switch box is good. Yay! That's a big plus as far as whether or not to go forward with the repair of this motor. Oh, you know what? I was just breaking down the whole setup here on the workbench and getting ready to put everything away, and it occurred to me, as long as I've got the 12-volt power supply sitting right here, why don't I see whether or not there's any life out of this starter solenoid? There is. Good. Sounds like a good one.